Okay, Kelly, take it away.
All right. Hi, everyone. Thanks for joining us for the ArmorFlex webinar. My name is Kelly Scott. I'm the Regional Sales Manager for the Pacific Region for Nilex. And I'm just going to go over a couple house rules here before I introduce Barry King. Please keep yourself muted and your cameras off. We will be recording this session and sending it out after the webinar. Let's try and hold all our questions to the end for a Q&A session with Barry. Now, if you have questions that you don't want to forget, please feel free to type them into the chat, and we will go and look at the chat and see what questions are in there and answer them at the end as well. So with that, I'd like everyone to welcome Barry King. So Barry is from Contact. He is the Eastern Area Manager for Hard Armor product line. Prior to joining Contact, Barry worked as a structural engineer for the city of Cincinnati and a bridge engineer for VDOT. Barry earned his BS degree in civil engineering from Colorado State University, as well as a BA degree in English from the University of Kentucky. Barry is also a member of the ASDSO and ASCE. And with that, I will hand this over to Mr. Barry King to take it away.
Hello, everybody. Thanks, Kelly. I appreciate you inviting me here, and always good to talk about hard armor, the solutions that are out there, knowing how destructive water can be, and especially in some of the more serious sites that we've all kind of experienced in our tenure. My agenda here today is just a brief hard armor history, kind of just how we lay out as far as Contech, and really, you know, our partnership with Nilex. And you can consider this seamless. What you see here in the presentation, you know, everything that we're subscribing to as far as ASTM International compliance, things like that. That's concurrent and consistent between the two partners here, Contech and Nilex. So I'll go over the history for a little bit and then get into the articulated concrete blocks, ACBs, talk about the applications, testing and design, installation, and some project profiles. And then Ajax concrete armoring units, CAUs as another name for them. Go over some applications for those, testing and design, installation, and project profiles as well. Mostly for this presentation, I'll be focusing on the ArmorFlex ACBs. So if you have any kind of question, I believe there's a chat somewhere that you can access. You can put it in there to log it in so you don't forget it. Consider this informal. If you really need to an answer right then, we can do that. But otherwise, we'll just save till the end. We'll have some time. So with that, I will get going. Legacy of success is what I like to call this. And then 1978 here on the left. That's kind of where you see these products start to come up in North America and start being introduced, knowing that across the pond in Europe, Russia, and some of the Netherlands, they've been using these systems for 50 to 100 years. Revetment blocks, ACBs, different names, but the same factor of safety, the same mechanism of failure. Here in the States, or here in North America rather, 1978 is where we started seeing them. And then you kind of go through the legacy there of testing. You see in 88, 89, the Federal Highway Administration saw the value in these and really started a research study. And then you see Ajax come up in the early 90s, and then the progression on out in 2013 is where this timeline ends. But since then, there's been development with the NRCS, again, ASTM International, you know, improving those standards. and things like that. So just to kind of give you an idea of the confidence you can kind of depend on when you're designing these. As a designer, there's risk involved, and not knowing where these systems come, and more importantly, not understanding how they are in factor of safety. I mean, risks associated there. So I'm here to clear some of that up and show you what these can do. Starting with the articulated concrete blocks, it's a flexible interlocking matrix of concrete blocks, uniform size and shape and weight, cabled together if you would like, for quicker installation. I should note that cabling is not required in the factor of safety as far as ASTM International is concerned. It is considered a redundancy. We'll get into that a little bit, but a lot of it is to do how do you test the tension actually happening in that cable if it's installed in a full-scale flume, say in the Netherlands testing lab, or Delft Laboratories, or Colorado State, my alma mater. So they can be used individually without cabling. There is redundancy there with the cable. So specific hydraulic capacities are substantiated by ASTM testing with not just the ArmorFlex type, but that is for all ACBs out there. Mattresses are hand placed, like I mentioned. And you can use them for a bevy of applications. Here you see scour protection. This is a full invert. And then shore protection, obviously. These are also qualified for wave attack, Plargic's equation for solving wave attack. That's kind of the guideline across the country, across the world, really, and what they use to size revetment when you're seeing shoreline coastal challenges. Flood control. Here you see a low water dam. This is out in Colorado, Fort Collins. And then here you channel lining. This is, again, scour protection, but you can really get a sense, this is in Missouri, you can really get a sense of the vegetation possible. So yeah, I mean, they're on the left right after construction, they're on the right 6 months through the growing season. That's what you have. If you look real close in that right-hand picture, you can see the block down at the water line. Weirs and spillways, one of the primary applications. This is an industrial application you see here, a CCR project, a coal power plant decommission into the Ohio River, discharging. And then emergency spillway protection. That's a bread and butter that we see down here in the States and across North America, really. And again, this site is more of a site where it's a park setting, but it had seen flow, it had seen flooding. They needed to get something that would hold up to this to the PMP event, and also have it aesthetic to match the surrounding park, and that's what you're kind of looking at here. And then just straight up, the dam overtopping protection. One of the reasons why these systems were developed and how they were primarily used in the Netherlands, Germany, and Russia over there. So here you're looking at a site that is fully vegetated. Yes, that picture on the right, that whole embankment, it has concrete blocks underneath it. There's 6 inches of loamy topsoil there. This is for the 500-year event in combination with a labyrinth weir. So very complex, done by Schnabel down here in the States. Downshoots. These, you saw the industrial one at the coal-fired power plant. This is a mining application, and you can really get a sense of the scale of what we're looking at here. This is in Arizona. I can't really name the owner here. They didn't really give us any kind of they didn't allow us to do that. Just these sites are environmentally sensitive. It's one of the times that I realized that there is a monsoon season out in Arizona and New Mexico, which was news to me. But yeah, these get tested on an annual basis. We have dozens of these long chutes out there performing in these reclamation projects daily. So, and especially during the monsoon season, Yeah, yeah, just quite a bit of flow going through these systems in those applications. Outfall protection, whether it be a 5-barrel pipe there on the left, or you have inlet protection there on the right. You know, we see these applications used in both scenarios. And then utility and pipeline protection. You know, this is DeRocha Marine out of New York, I believe. They're building this in San Francisco. And so this is a cable slash utility slash communications pipeline going across the bay. You can see what they're using here, the 8.5-inch block with the submersible bar. Just a little bit of everything with these systems, the ACBs, and they're another very typical application that you can see. You know, when you're talking about boat ramps and low water crossings, you do want to think about your saturated soils and the need or what do you use for subgrade improvement there. Saturated soils don't behave very well for wheel loads, depending on the soil type. So typically when we see these, there is some soil improvement, i.e. crushed clean stone, maybe a layer of geogrid just to lock everything in and just to speak about longevity there. So yeah, another very typical application. Low water crossing, same thing. This is a ranch down in Florida, and just to get across the canals there. But all these applications, they have to be based off something, right? And so testing and design as engineers, as specifiers, that's very important. So you want to know the capacities of these systems you're using, whether it be a steel I-beam, a concrete channel, you know, girder, or, you know, ACBs as erosion control. You want to know what they can do. You want to know how they've been tested. What are the redundancies there, and how conservative is the design? So things like that that we'll cover. I will speak right now about ASTM International. This is an international standard. Well, it's an international standards. You know, they bevy of standards from asphalt, bituminous asphalt, or concrete, or you know, saline freestall, and all the different testing regimen that are highly vetted by this organization. ASTM compliance for ACBs, articulated concrete blocks, put in hydraulic situations. It's the same thing. You want to know what they can do. When is the water going to overturn your system and move it down channel? Do you want it to do that? I don't think you do. If you did, you would use something that is more prone to that kind of movement. So when you're talking about ACBs and you want to know what they can do hydraulically, you have to look at compliance testing. And there on the left is D7277. That is the actual test, what you do, how you set it up, what grades you put your block on. And these are all full-scale tests. And so for our example, we were at 2-to-1, 115 feet long, and we put 5 foot of head on this dam, or on this channel, 5 foot wide. And the resulting velocity was upwards of 35 feet per second with shears of 20. So very strenuous hydraulic conditions there. And with that test that you're seeing there on the left, you have to marry that with the standard on the right, which is D7276. And that is, you have done this test, physically done the test, and now how do you interpret that? That is critical, because you don't want that up for interpretation, right? There's one way to test it. There's one way to interpret the results. Both of these take care of that. And it's really revolutionized these as far as what they can do, and really up the bar as far as how these systems are viewed hydraulically across the municipalities and the states down here, and at the federal level. So again, ASTM compliance testing, very important. It's worldwide. It's an international standard. Again, just to hammer it home, it's my one soapbox. You know, you have your parameters, you know what your soil is, you do flow duration. So you do 1 foot over top ring for 4 hours. You check and see if there's any damage. You keep going until you have defined failure, which is loss of intimate contact. So that is the system itself lifting off that subgrade. And that's what they measure. And then you take those, and again, you take them into the next standard, D7276, and that's where you're doing the interpretation, determining the mannings. What is your critical velocity? What is your critical shear? Things of that nature that actually are good to know when you're designing hydraulic structures and the like. And after all that rigmarole, and thank you for listening to my diatribe on testing. It's very important across the international design community. You will get something like this. This is Colorado State, Dr. Chris Thornton, director of that, and you will get the capacities. Now, this is the summary sheet, so it is a report about like this, detailing exactly what was done, how it was interpreted, and following, as dictated by those ASTM standards we mentioned earlier. There's one way to test it, and there's one way to interpret it. That this is kind of what you get. So if you look down there on the right, we have 35.5 feet per second and 20.1 pounds of shear. Okay, at a 5 foot overtopping. That is that's moving some water. To give you an idea, I am, and I'm going to be kind to myself since it's right after Thanksgiving, but I'm about 6 foot, 200 pounds, and rule of thumb is 6 inches of water flowing 10 feet per second would take me off my feet. That's how powerful water is. Everybody's done that. Everybody's stood in the stream. Depends on your stance, obviously, but in general, that's a good rule of thumb. Here we're talking about 35 feet per second, 5 feet deep at the head box. Okay, so that kind of gives you, puts your head kind of where that, what that means physically speaking. And then when you get through all the testing, you get your assigned your capacities for your system, whether it's ArmorFlex or another system. Again, everybody has to subscribe to this if you're going to use these. You have to go with your design methodology. NCMA, which is the National Concrete Masonry Association. I put that up here because that's the easiest to digest. And what I mean by that is I always encourage designers to look at the math, and you can actually do it by hand with your project that you have, and see for yourself what it means. And excuse me, quite frankly, the conservatism that's built into this method, I think it will really, if it's the first time that you're using them, this is a good guide to go with, and it does a step-by-step a punch and factor of safety, depending on loss downstream, all those things. It's no different than what you're going to find in the federal documents with the U.S. or even, over in Europe. I mean, you are going to see the same math. This is just a good, user-friendly way to interpret it and work through it. So that's why you see here. It's the factor of safety is what it is. Typical cross sections, a standard cross section there on the left. A lot of the units have that, and you're seeing the subgrade there, the geotextile, and then the revetment, right? I've heard it called artificial riprap, which, okay, I'll accept that. But, for this riprap, every rock is the exact same size. There's no gradation. There's no, hey, we'll lose a little bit of this over time, and this will fill in, or maybe it won't, or we'll just dump more rock in there. Depending on where you are, that could or could not be okay. But yeah, the D50 for each of these systems, each of these SKUs of thicknesses. There on the right is the tapered series cross section, and the only difference there is you're seeing a 4 to 6 inch drainage layer, and that's just clean stone, minimal fines, and that's for the high velocity flows. That's for those spillways out in the monsoons and in New Mexico, and for those steep channels, down in Kentucky or up in New York that we're seeing them. And really, Pennsylvania is another state that has really put these to the test as far as, okay, let's build this. And not only are we going to build it, but it's going to see water on an annual, if not biannual basis, and it's going to see the design discharge. And so seeing that happen really gives you a lot of a comfort that everything that you're seeing and working through the math and all that stuff is really worth it and actually true. So contractors build these all the time. It is a dirt job. You're moving dirt to existing or proposed contours, and then you're laying a revetment on it. It really is that simple. So the critical thing, and there is an ASTM standard for this as well, is construction. So again, moving dirt, getting proposed grades, hitting those grades, doing some fine grading, making sure your grades are good, and then putting a revetment on top of it is really what we're talking about. So on that tapered cross section, you see a 1/2 inch fall. Think of shingles on your house. So when you're looking at a tapered series rather, I mean, that's one of the differences from a standard block there on the left, standard system. And again, that is dictated out of the factor of safety. If it doesn't work for the standard cross section, you're going to look at the tapered series. And guess what? If it doesn't work there, then you're going to know that as well. And you're going to be like, hey, anything short of casting a concrete gutter, that's probably what you're looking at if you can't get a tapered series to work. So moving on from those a little bit, just giving you some permissible velocities. I mean, really, that is what we see ACBs functioning, 8 feet per second to 35 feet per second plus. That's quite a range. And you're just talking different thicknesses, right? The thinnest and the smallest footprint system we have, and that Nilex is offering in Canada, you're going to be about the 8 to 12 feet per second. But they also will be able to offer the 35 feet plus per second as well. So all those things can be covered. It depends on the performance of the site and how it's analyzed. So Cast in Place does a good job. Riprap does a very good job. I put an asterisk next to that. We can talk about that. Again, riprap ditch lining, but bare soil even does well for a little bit, right? So let's talk about that. As far as riprap, this is a generalized factor of safety in comparison to rock. Okay, and so what you're looking at there, this is the core method for sizing traditional riprap. So looking at this visual here, so on the left, you'll see 12 inches. So the Army Corps of Engineers, this method of riprap sizing for 10 feet per second, you're looking at a 12-inch rock. A 4 3/4 inch, and again, English units, I apologize, but yeah, I mean, that's they can both operate there, and that may or may not make sense for 10 feet per second, but then you get up to 21 feet per second. There in the middle, right? You have a 64-inch section of riprap, okay? And a lot of times, half of that is they expect it to move. It does move, and so you'll actually put a double layer there because the rocks are undersized because there is a gradation involved, right? You'll lose some of the smaller stuff, and then the bigger stuff starts to tumble. I mean, this is a mechanism that we see and that I used to see at VDOT, Virginia Department of Transportation. We used to dump rock all the time. It was one of the big expenses of our district. So this is, again, just a nice visual to show you as you move up in velocity and more severe environments, these systems make more and more sense. They can not only save money by material, but imagine hauling all that rock. I mean, that, especially nowadays, I mean, that costs something. So to look at that cost benefit of what can be done there, that's really what kind of can swing a project sometimes, because budgets do mean, if not everything, they mean a lot, right? So installation, manufacturing, let's look at that a little bit with these systems. Sorry about the ASTM stuff, but this is a standard there on the left for the manufacturing. Like you have to be in compliance with this. You know, to be on these critical structures, they have to meet, the materials have to meet this criteria. Oh, you have saline, you have salt water. Okay, there is a caveat in here for the saltwater mix. So all those material properties are captured and addressed. Okay, and then on the right there, that is the installation guide. So again, there's a standard for everything, almost ad nauseum. But in this case, it provides comfort, right? Because you are used to using rock and maybe cast in place and some other materials. And so you want to know that this isn't just something just out there in the ether. This has been vetted, and there is a way to manufacture it. There is a way to place it. Again, a big dirt job, right? It's all about having the competent dirt and getting those proposed grades hit, and then you armor them with something for the design flows. So another slide on ASTM manufacturing. Everything's covered there. QA, QC. It's all listed, the cycles and the molds. And then 6884, that's the installation. You know, there's not a question. Hey, is this okay? Well, let me see. Okay, yes, that's okay. Or no, that's not okay. You have to get it to this compaction or whatever that is. So ACBs according to ASTM. So you hydraulic test them, international standard. You run the analysis on that testing. There's an international standard for that. You do the design. There's many, many methods. I showed you NCMA, you know, names for the method. They're all the same method. The factor of safety is the factor of safety. The numbers are the same. NCMA, easiest to follow. But that's what the ASTM input. You have to have the input from the previous testing to use that method. And then you go to manufacturing. Okay, how are we going to make this? Do I make it like this? No. There is a manufacturing specification, very stringent for it, compression, absorption, any of that stuff. Installation, again, same thing. So thanks for listening to the ASTM part of it, but it is very critical, and you should know that that does have bearing on what these systems can do and how they are used. So project profiles, see some things that were built here. Near Herbert, Saskatchewan. I like this one. The Highland Reservoir is really, it's a flood control system. That was really the problem here. And you have various levels of protection. And what I mean by that, if you look in the left-hand picture, up there in the top, you see that green. So those are where the hydraulics aren't as severe, right? And you can use maybe a softer armor, something that's more cost-friendly to the site, because you don't need big bad ACBs or ArmorFlex, because hydraulics don't dictate them. And that's really what you need to understand about what to expect from Nilex and Contech, is that, you know, over design is fine, but budgets are budgets. And so to recognize where a softer, less expensive, high performance turf reinforcement mat or something like that, to identify that and recommend that for the site, whether it's on the engineering side or on after it's been bid, that's critical. And that's what you're going to get here. That's what I like about the Highland. You're using a little bit of everything here. It had a tapered system, combination solution, like I said. The support were the specifications, running the factor of safety, contract drawings, working with any kind of on-site installation assistance that was needed. The outcome, and we would know if it was bad, the efficient installation, you know, always finishing early. And you know, we were stressing the termination and transitions to other systems. That was one of the outcomes and one of the things, you know, everything interesting happens at the boundaries, right? And so you're going from, say, a high performance turf reinforcement mat to an ACB or ArmorFlex system. What does that interface look like? And so all those things were brought to the table by Nilex, and something that, frankly, they do on a daily basis. Jensen Dam, something more project that's probably more recent, a little bit more recent. McGrath, Alberta. You can kind of see the project location there on the right. This is a really good shot that was taken. A lot of things going on with this project. The history of it, it's the historical history of this site and what went on at Jensen Dam. I believe it always saw some kind of water. It was planning, with the redevelopment or what was going on in the surrounding area, that more water was going to be directed into this area. And so they needed to make sure that they had a weir or a channel, a fuse plug design that would work and be able to pass this on a consistent basis. So at Jensen Dam, this is really what you're looking at in cross section. Design challenges. The access was remote. The weather was tough during construction. And the timeline, it needed to happen fairly quickly. So you get all those all together, and it makes for some nervous contractors and nervous suppliers, because we want to make sure everybody's hitting on the same cylinders and in lockstep there. I mean, we really want to make sure that we know what each other are doing. With the manufacturing, same thing. So having that dance going, and trucks coming in and delivering material, and that being set, and then more trucks replenishing, that's really what we shoot for, and what happened here on this site in McGrath. It was a 70T system. It was a tapered system for the hydraulics, channelized configuration, as you can see. The support with the contract drawings, on-site installation assistance, and our engineering services. There were many iterations of what was okay. So, hey, we're going this wide or this wide, and do we still pass factor of safety? As we all know, plans from the ministry, or in my case, the Department of Transportation, Federal Department of Transportation. When I see plans like that, it's construction in heaven, right? I mean, we all know this as professionals, and in this construction business, plans are great. You got to have a guideline, and they need to hold that as much as possible. But things change, especially in these big dirt jobs, and so you have to be responsive. And that's one thing that I'm proud to say. Nilex and Contech are quick to see those problems that can mean cost on site, and to take care of those expediently. More pictures here. You can see what's being done. See the snow in the background. I like this picture because it's conforming there. You can really see the articulation on the right-hand side. There is a big crane there. It doesn't need to be a big crane. We commonly see excavators placing these systems. This was hey, we're going to set up here and reach everything, and they had it on site. So that's what happened here. And just more setting a mat there on the left. Pretty simple. And then there on the right, they have the grout seams there are being, they've been poured, so those are being taken care of there as they firm up. But an all-around great job by the contractor and by Nilex in particular, just because it was cold, material needed to be had, it needed to happen. There was no question, and it did, and everybody got on board, and just a really nice installation in early 2001. So here's another application, Banff Legacy Trail flood repairs. As the flood went through there in 2013, there was a really bad event that came through this area. And I know Calgary is seeing, that design being implemented now, and what's going on around Calgary is similar to what this experienced. But in June 2023, they blew through here and just destroyed this whole area. And they needed to rebuild the trailway, and that's what you're seeing there. There's on the right-hand picture, you can see it better. There's a trail, and it's kind of, you know, paralleling that road. And it's, you know, cyclists are through there. You have this grassy slope, and so after that got blown out, after all that rock moved on the slope, they wanted to come back with something that would really promote some vegetation. And so what you're seeing there in the left-handed picture, they're marching down station with the open cell ACBs. They'll be, you know, backfilling with loamy topsoil, as you see on the right, with the ultimate goal of growing in your native grasses and wildflowers. You know, that's always something that I get a question on. It's, you know, if you plant those in the beginning of, in the middle of August, say in Mississippi, you're not going to get much growth. So adhering to the growing seasons, you know, oftentimes we'll see ACB open cells being placed in the winter and not being backfilled until the growing season or seeded, because everyone knows that you're not going to grow anything in the middle of February. So a very beautiful area and a very successful solution there for them. XL Alberta, channel lining, bridge scour, a little bit of both here. You can see what's going on there on the right. It is, you know, it's about that train and about that infrastructure coming through here. It's a large drainage area, very flashy conditions, critical infrastructure, like I said. ArmorFlex 70T, large riprap transition, as you can see there on the right. So in the less effective areas, flow ineffective areas there on the top of the slope, that's where you can get away with something that's more dissipative. And again, same support, same outcome. Well, the efficient conveyance here on the outcome. I mean, this fills up quickly, and they needed it out of there. And so a little bit less roughness with the ACBs provided that. It's not much rougher than the rock around it, but enough so where you can play with your depths and make some efficiencies there. And in this case, it made the difference in the design. So yeah, that's what I have for Ajax right now, or for ArmorFlex. And again, you know, just a really efficient system to get down, you know, with Nilex and Contec. I mean, you're looking at everything from layout drawings to, you know, factor of safety calculations, you know, all that stuff is available. And it's really about improving the confidence and improving the conservatism of these systems across and what they're kind of adhering to. And with that, I'm going to look at the chat. Okay, real quick, I got these questions on the ACBs. Is there fill in with the grid in the second section? There does not have to be. So that, and this is by AS, is just gives initials here. But that's a great question, and I'll go back to the installation. That's ASTM D6884, which is the installation guideline. It speaks directly to the fill. There is geogrid in the second section, and that is in those higher velocities. That's those stones. They could have the potential to be excavated out through the open cells. And so to have a confining grid there, it's not for strength parameters or subgrade improvement. It's really a screen to keep those it's the gradation on the rock is 1.5 to 2 inch minus with no fines. That's what you look for there. So and then I have another one here, Sam Sue, for the tapered series cross section. For a drainage layer, is there grass on top, which indicate topsoil in between? Yeah, and so that's, again, Sam, that kind of speaks to the same thing. It's what you want to do as a designer, you know. We see these systems unvegetated, unbackfilled all the time, because what happens in the field is that you get settlement of rainwater and sediment and everything else. They end up filling these in over time. And then you get the gully washer through there, the design event, and it discharges all that sediment, gets it downstream. So the point being is that it doesn't need to be there for the system to work to meet that factor of safety. It's more about your eyeballs and the aesthetic and what you want in the finished condition. Let's see. Okay. And what I'll do, I'll just move on right now. Great questions, very common questions that we get. So let me go ahead and close that. Yeah, there we go. Okay. Ajax, what are they? They're funny looking. You played with them when you were kids. Just kidding. I'm not from the 1940s. All joking aside, they are an energy dissipation unit. And I'll go through this quickly. But they're really something to look at. And by all means, very effective. Interlocking high stability armor units, they come on pallets, they come on skids, so they're easy to get to the site. You do random and uniform installation. The only difference is with random installation, you'll probably use about 5 to 10% more. Uniform installation is actually quicker to install and you use less units. You can do hand place or bundled placement, put them in groupings, like you kind of see in that top left-hand picture. It's a very rough layer. And what I mean by that, if this unit is fully exposed in the water column, it has a roughness of 0.1, okay? But how they're commonly used, we'll talk. So that's fully exposed, water blowing through it. That's how they're tested to get their capacities in full scale. 2 foot, and that's from tip to tip, they lay down, okay, when they're installed from tip to tip, 2 foot, 4 foot, 6 foot, 8 foot, and 10-foot units are available. Very rarely do we see anything hydraulically beating or overtaking the 4-footer. So just hydraulically, when you get into the 6, 8, and 10s, really that's about geometry. And I got to armor this big bank, and instead of using a bunch of 4-footers, let's just use the 8-footers and get to that 50-foot scarp in Alaska for Chevron, which is one of the applications that was done. So Ajax, scour protection, pier scour protection, right? And abutment scour protection on existing piers. Energy dissipation, this is a agricultural application there downstream. They turn this sucker on. They have to get it to dissipate and before it goes downstream, because what was happening, it was tearing apart the sandy soils downstream. Velocities were too high. Tow stabilization, yeah, they're on the left. You can see kind of the softer cocoa mats being done, and then right at the waterline are the Ajax. I mean, you see that in a lot of fill applications, or where they do impoundments or drainage areas or retention basins. I mean, you'll see that at the waterline sometimes, and so that's where you're going to see erosion. And what'll happen is that it'll eat away at that. The bank will get steeper and steeper, and then it'll fail, and then it'll happen again, right? And so you get that backward encroachment into whatever. And is that important? Is there a structure there, or is that something like you see on the right, where you're a little bit more, it's more of a rural area? So it depends. Ajax, the drop structures, all kinds of configurations you'll see to dissipate energy. There on the left is downstream of a weir. There on the right, that really is the application you're seeing there in the background there. They needed to smooth out this flow in the design event because it was tearing up this detention basin. Breakwaters. coastal wave protection and testing. So to get into the testing, everything from wave attack testing to channelized testing, all of that has been done with these systems ad nauseum. The structural analysis was done in Auburn, the impact testing, I believe that was done at the University of Florida, stability testing, the University of Florida, wave attack testing, that was by the Delft Laboratories out of the Netherlands, and pier scour testing, that was done by Oregon State University, a gentleman named Bill McDougall, who was the forefront and one of the forefront people in wave attack design and countermeasures. So yeah, factor of safety methodology, velocity and shear, the biggies with when it comes to hydraulics, right? What's your velocity and what's your tractive shear? What is shear trying to scour out of that channel, right? So design, I wish this was really earth shattering, but it's not. I mean, it is a particle in space and you're trying to overtake that particle and roll it downstream, right? You have a lift force, you have a drag force, you have the brothers and sisters, other Ajax rather, rubbing against them and creating some friction. The only thing that is stabilizing, the only thing that we know is the interblock restraint and gravity force normal to the slope. Everything else is the capacity of the system. So it's about rotation. And if you think about it, these are set in a continuum. It's very, once they are in this kind of permeable matrix, very, very hard to dislodge. I've seen them go way above the design velocity and be just fine. So it's intuitive, right? You have this jack and they're kind of all bunched in together, but water can flow through. And so it's intuitive. It was for me. And then when I saw it tested and actually see it in use in the field, it becomes very obvious. So for pier scour, HEC 23, if you haven't heard that before, that is the pier scour guideline for existing structures here in the States by the Federal Highway Administration, design guideline 19. I can send that to you. And that is, hey, I have an existing bridge, got some massive scour. I have been putting rocks in here for months and years, and they're all going downstream. I need something more permanent. That's when you need to start looking at these systems. A project profile, Lewiston, Idaho, you can see what's going on here. It's one of the 10 most scour critical bridges in the state. I mean, it was going to lose their piers. They were getting massive scour holes. And so, yeah, they installed inflowing water in bundles. So you see there on the right, that's a submerged bundle on what they placed. This actually won an award. I went back to it because it won a state award and really a national award because they monitor this yearly. We look at the reports and you can't see the blocks anymore. They have bed material over them. They've disappeared, but they're still there. They haven't moved. The elevation at the top of the bundles is still the elevation today after, I think these were put in about 12 years ago. No, 15 years ago. So yeah, they have been intact for that long in the scour pad that they were developed for. No more scour holes out there. So it doesn't work everywhere, but when you have a problem and the maintenance is becoming unattainable, something to look at. Hosworth Bridge, Red Rock Creek. This is a design that we assisted in. Unclear of if it was built, Northern Region, BC. Believe it went to tender. But just a very good application. You can see where this is located, fairly remote. They had this bridge structure. They had seen massive flows through here, and it was, let's face it, some of the bridges weren't wide enough, and we all experience this no matter where you live in the world. Sometimes, a shorter bridge, that's what we had the money for, right? And so that happens. And so when you have those applications such as this, and you're seeing the traditional methods like the rock going away, which what was happening here. You need to look at some other things. In this case, yeah, it's a combination. So on the upside there, or the top of the page, you see a big where the riprap is curving, you know, that big riprap section there. And then on the downstream side, you also see it. But inside the barrel there, where the foundations are, the rock wasn't staying. And they needed to go with something more beefy. So the designer at McElhaney contacted us. This is the section they went with, and it absolutely tailor-made design and application for that system. You know, I hear from contractors, wow, these are really odd looking, and how do I mean, it's usually about a half hour into the pre-con, or we have a discussion. They're like, oh, is that it? They're that forgiving? Okay. Because the spacing is acceptable and different. And so you can place them, and they might not look perfect, but they don't have to. Okay. They are made to be redundant and take some heavy velocities. So that's what you're seeing there. I wouldn't be doing my job if I didn't include this, the granddaddy of all rivers down here in the States. When I say bundle, that's what you're seeing there on the right. And it's the Mississippi River. It can move some water. It has some power, not just velocity, but stream power. You know, that combination of shear and velocity, that momentum, just wanting to take everything and just push it all the way down to New Orleans. I mean, that's what it wants to do. So you need something that can work with that, accommodate that shear and velocity, but still give you the protection that you need, i.e. stay in place. And that's what was done here. The 48-inch Ajax bundles, they were 48-inch units. So laid down, they were 3 foot high. The size of rock that was designed for this, I didn't include it because it almost looks too ridiculous looking at it on a presentation, but it had multiple D50s, and the total section that they used that was proposed that met the factor of safety per Hec 18 and every riprap equation you want to talk about, it was upwards of 12 feet thick. And they were going to have to excavate down, dredge. And so to look at Hec 23 and know there's another solution out there, and to get that put in and watch it see the floods that have happened in the last 2 years, and these are exactly where they need to be and where they were set, is really satisfying. So yeah, this was a big bridge. I say that just because of the Mississippi is so mighty, and I know that they have mighties up in northern Alberta and all over Canada. So just know that even the strong stuff, we can combat that. We can possibly help you out. I mean, that's what Nilex and I are here for. At Contech, we look at design. I mean, it's site solutions across North America is what we're trying to do. We truly try to provide engineers with technically focused recommendations. When you get a spec from us, it will be performance based. We're looking for the performance, you know, we're going to preliminary product recommendations, cost estimates, analysis, specifications. Again, that's going to be a performance-based spec, which means an open spec, as long as you can meet the hydraulics or what is the needs of the project. Permitting, we assist on that as we can. We are not experts on those, but we have a lot of people in this building and across the country here that are experts. And we work as a team. Installation, again, I mean, a lot of things to draw from ASTM. There is a way to do it, and providing that guidance and quick guidance while someone's on site to keep the project going is, I think, imperative, and something that we all can probably identify with. That's really what I have. I mean, that was a lot in a short amount of time. I do appreciate you guys having me. And I'll entertain any questions whatsoever. Glad to do it. I do see someone here. Okay, yeah, Alan Strecker. Okay, here's a question. I'll make sure I got. Okay, yeah, Alan, how big were those Ajax in the test flume? That is a very good question. So we tested 24-inch units in the flume. Okay. Couldn't move them a micron. And so we reduced it because there's a thing in that in Colorado State in the testing, you know, across the Delft laboratories, that Froude scaling that they use, that I always have to have Dr. Thornton run me through. But yeah, and so to extrapolate up using the Froude scale, they ended up really getting the best capacity out of the Ajax. They made 6-inch, they made quarter scale in 24-inch units. So they were actually quarter scale. They were 6 inches. They were made of concrete, so they had the right unit weight. And they tested that in the flume, and the 6-inch units, they handled 15 feet per second when they were, and so, you know, they weighed like 5 pounds a piece, and a 24-inch unit is 75 pounds and it's 24-inch. So I'm not saying you just take that and it's not a linear relationship, right? But that gives you a sense of what was done. So I hope that answered your question there. We tested both, got most of the capacities. Once we kind of maxed out the water we could put on the 24s, we went to the scales, and then we really tried to fail them. And that's, there's a Dr. Thornton, there's a method to have a conservative value on that by the ASTM. Did they try to drop a geotextile on the scour before putting the HX bundles on the US 95? Great question. So let me go back in time. So if you look at that bundle, that's one of the things, and you're really picking up on something here. You can incorporate the geotextile with the bundle. And that's what you're seeing there. Okay, and then in between the bundles, there's tolerances because there's some bunched up overlap there. And so by the applications that we've seen, by the scour reports that we've installed these on, that there's a 4-inch clear space that you can put between bundles. And I know I'm getting in the weeds here, but this is a very good question. You incorporate the geotextile with that, and then there's tolerances in between the bundles. It's 4 inches usually. That is acceptable and proven, because in those little voids, everything's so rough around it, you just can't get any velocity to move in there. So let's see here. Sam, thank you. Yeah, and you can contact and Sam here is for ArmorFlex product. Who should we contact for technical questions for price goods? Please reach out to Nilex first. Know that I am. I mean, they're your first call, and know that I am right there behind them. That is my job. But the relationships up there with those local folks, that would be the first place to start. I'm located in Cincinnati, Ohio. I travel all around the U.S. For these systems and internationally for exactly what you're talking about. Well, for projects, but yeah, you know, just know that you contact Nilex. Any questions they have, or if they need any more expertise, they're going to come to me and my team. And if we haven't seen it, we're going to go straight to Colorado State and the people at the Delft laboratories to get the big brains on it. So hopefully that answered your question there. Let's see. I think that's it. Again, thank you all for having me. And Kelly, I'll turn it back over to you, man.
All right. Thanks, Barry. Turn that on. There's no more questions for everyone, for Barry. I'd like to thank everyone for joining us, and hopefully we got some more coming webinars soon. Barry, again, thanks a lot. Always very informative.
Thanks. Great presentation.
No, I appreciate it. Thanks, everybody. Yeah, if you need to contact me directly, I can do the end around denial-X, and that's fine. But we're all about solutions and working together. So thanks again.
Thank you.
Excellent. Thanks, everyone.